Yeah.
Welcome everybody. Today we are talking about the revolutionizing vehicle development with the real-time simulation and HiL testing. We will also cover some aspect about the model in the loop, software in the loop. So in a wider range, we will talk about XIL and real-time simulation. Let's start from some context analysis. The context analysis will talk about what are the challenges today on the automotive segment. First of all, we are raising new vehicle architectures where by 2030, the 60% of new cars must be electric or electrified to reach the net zero by 2050. We have an increasing complexity of controllers in the vehicles since the new technologies are raising ADAS, are connecting vehicles, electric vehicles. The complexity of the controls is a very important factor. New disciplines, ADAS becoming part of the cars. L3 now is a new standard, and with L3 comes a lot of sensors that must be installed and controlled by the vehicle. Software-driven development. Nowadays, passenger cars and vehicles in general are complex systems and control units with several control units, but basically are softwares on wheels, with reaching right now more than 150 million of lines of code, and this trend is still increasing. And then some disciplines getting more relevant. For example, NVH is getting more and more important into electric vehicles where the internal combustion engine noise is not there anymore. So what are the other problems? Physical testing is becoming a bottleneck because of the new architectures, increase of complexity, and everything we said before. What does it mean? Here are some quotes by our customers. See the physical testing, why are bottlenecks? Because they're expensive, because feedback comes too late, the weather dependency, the normal delivery development time is not enough anymore because of the short-term delivery time, and the weather is becoming more and more important because there is not enough time to test in weather conditions or in hot conditions the vehicles on the road. It is not flexible because normally modifications are expensive. You need to have physical parts to be modified on the prototypes. Most of the time it never works the first time, and then it's downtime. It's very important, and time means money. And of course, it's difficult to manage the increasing complexity on multiple prototypes and multiple vehicles at the same time in parallel. But having said that, we still need to remind that everything is about the driving experience, and everything is about people. A driver, it's at the end who decide to buy or not to buy a vehicle. That's why it's important to define and validate targets for driving experience since the early beginnings. It's important to assess the driving experience throughout the development processes. And it's also important to develop a car that will be accepted and appreciated by customers early in advance, and having possibility also to have clinic events to evaluate even a vehicle before building a prototype, and then direct the development in the right direction. So to do that, what VA Grade can offer? What is important is that to use the right simulator that is can be scalable, because it's VA Grade offers a desktop simulator, from desktop simulator to large dynamic simulator, going through static, NVH, full spectrum simulators. It needs to be multi-attributes nowadays, because as I said before, NVH is becoming a very important part of the development and need to be integrated into a driving simulator also to assess vehicle dynamics. And also, as it needs to have a wide performance of range for covering the entire spectrum of frequency. A right simulator, but also the right models. Right models means that from early beginning of starting of the project to the end of the project, with the evolution of the complexity of the models, of the digital part, and the introduction of the physical components when they are available, it's possible to use on the same, exactly the same stack of platform, on simulation platform, the same instruments, the same devices, just use and interchange digital with hardware parts when it's needed and when it's possible. So the right level details, the right mix of model, software, and the hardware in the loop, and of course, the progressive improvements. So what Claudio means really real time?
Yes, Alessandro, a real-time system is something that can react to external excitations fast enough to influence its environment with correct informations in the right time. So having this capability, the real-time system can allow for a marriage between the physical world and the digital one. So with the HiL approach, everything in the loop approach, we can think about a testing augmentation in which the vehicle model becomes the pinpoint of the whole development process, starting from the beginning, from the concept, up to the sign-off. Having the same language in the whole company, across all the departments of the company, and this language is the vehicle model, the communication becomes very clear and very lean, and we can focus on the interaction between the different components, and even integrating a complex vehicle function become easier because everyone can focus on the single components and have a clear interface surface with the others. Everybody knows the typical V cycle. In the V cycle, you know that you have to focus on vehicle level definition, system level definition, and then component level validation. And this is a very long journey up to the sign-off because it requires a lot of effort in developing functions and so on. The digital world and the mixture between the digital and the physical world allows to shrink together the two branches of the V. And so someone calls it like bridging the gap between testing and simulation, but probably it is more than closing the gap, because the real-time models of the vehicle and the real-time models of every subcomponents can be as proxy of the physical things in any phase of the development process. But what are the tools that VI Great put in place for this process? Alessandro.
Thank you, Claudio. So at VI Grade, we elaborate a simulation platform. What does it mean, simulation platform? We define, in order to shorten the V cycle, an HiL solution that is called outo that is able to accompany customer and engineers from early stage of design, concept design, to the final sign-off of the vehicle with the same, exactly the same platform simulation, real-time simulation platform. We will then cover in the next slide some of details, but basically the idea is to follow all the steps of the V cycle from the desktop simulator with offline simulation and model preparation, in lab simulation with software and the hardware in the loop, never forgetting the model in the loop when hardware and software of the ECUs are not available, on sim together with driving simulators. The on-vehicle also solution able to run real-time or even faster than real-time vehicle models inside the vehicle on the road prototypes, and then the full digital twin. We define three main application areas. The first one is the chassis. The chassis is for a vehicle dynamics engineer, is the bread and butter, is the main focus since many years. But all these categories and areas are, of course, interconnected between each other. When we talk about chassis, we talk about steering, dampers, suspension systems, there are active or semi-active suspensions, brakes, with also steering and brakes that could be ride-by-wire systems. Then all the controllers and active aero. Then we have the group of ADAS, autonomous vehicles, and the UX UI that we cover on under the same umbrella. Means that all the sensors like LiDAR, camera, radar, vehicle in the loop, vehicle 2X, and of course all the HMI and the user interface in the vehicle. And then the powertrain and driveline area, where no matter what is the type of powertrain, it can be internal combustion engine, hybrid, fully electric, with battery electric vehicles, or even fuel cell electric vehicles. All these are covered by the powertrain and driveline area. What we do in order to cover the real-time simulation, we define a standard platform in order to run real-time simulation and real-time vehicle models on it. We define a bunch of standard configurations that covers the majority of use cases. We started with an 8-core system for desktop simulator. Then we moved to 16 and 24 system that can equip a very complex hardware-in-the-loop system or a driving simulator. And this year we launched the new outo 24 with upgraded performances on the CPU. And then also I'm glad to announce that we launched a brand new products for 32 and 64 core machine, where with a very new CPUs able also to assign a specific task on each core of the CPU. And what is important also that these specific autos are being designed to run multi-body models. For example, SIMPAC or Adams real time, and still also able to run simulator, driving simulator, complex one. And then, of course, on case-by-case studies, we also have the possibility to build a fully customized solution. In any case, every single auto is able to be expanded with multi-I/O boards covering the majority of automotive standards in terms of protocols, so FlexRay, CAN, NetIOs, and digital and analog signals. Another novelty we have launched this year is the auto on board with the same computational power of an auto that can be used on a rack or a desktop simulator. We can also fit within a car with, of course, a form factor much smaller and slim, with a nice carbon fiber cover, and is a rack solution with a 12-core system and a Xeon Gold CPU. What is the ecosystem? We talk about the platform, simulation platform. And what we call simulation platform means an ecosystem, open ecosystem, where we can run both VI-grade products in terms of simulation software, but also third-party software, starting from vehicle models. Of course, we can run a VI car time, but also we can run, as I said before, multi-body models, but also simplified models like Daimler, IPG car maker, tire models, very important. This is becoming more and more important to test different tires and before selecting and building the first prototype. And thanks to the multi-core technology, we can also launch specific tire model on each wheel in real time. Different scenarios, driver models, sensors. We can link the auto system to external third-party controllers. Customer can have different systems for linking ECUs and traditional hardware in the loop systems with NI, space, vector, and then we directly link in real time to those systems. And sound, force feedback, telemetry, biotelemetry, motion cueing with different platforms, and all runs in real time on the outo system. What, let's say, in a more precise way, what does it mean, outo and a simulation platform? The platform is formed by hardware, with the specification I listed before, with the real-time machine, of course. Then we can have a signal conditioning module, 14-section modules when we build a rack, with all the I/O boards, programmable FPGA, for example, and then all connections. Then we have the simulation workbench layer that allows us to define which are the tasks and also to create the network of input outputs to link with the ECUs or mechanical components, or simply linking and running real-time Simulink models on it. And then we have the drive sim stack of software with VA-grade proprietary systems, but also the possibility to link, as I said before, with the external FMI, FMU, and OpenAPI system to third-party software. This, of course, comes with a testing automation that a case-by-case study we can build that it helps to link the device under test for a mechanical hardware-in-the-loop system, and of course with the real vehicle when we talk about onboard system and with the driving simulators. Please, Claudio, can you show us what are the use cases?
Sorry, Claudio, you're on mute.
Sorry. So thank you, Alessandro. Everything typically starts from the model in the loop. So typically, we don't have yet a prototype of the system, and we have to start discussing about the things that need to be installed in our vehicle. Here, there is a short example of a model-in-the-loop approach in which we are in the very first phases of the development of a steering assembly, and we have to decide which are the targets for this steering assembly. So everything starts with a mathematical description. We start building up a mathematical model of the components, try to find the best compromise between the complexity of the model and the reliability of it. If it is not the first model of the steering system that we have to discuss, we can also compare the results of our model with some previous experience in the real world, and then we can start playing with the parameters and try to figure out what is the best for our model. You see here that everything is very flexible because we have just a mathematical description and we can play with the numbers. So the methodology of the test will be the same during the whole test, and we just change the parameters, and this procedure will remain the same always, even later when things becomes real. So we can compare different tuning, and we can compare different mathematical models. After the comparison, we can even put the driver into the loop, and so to keep together both the objective assessment and the subjective assessment. And this is the key point. So we have a real-time model that it is capable of running in a driver-in-the-loop scenario, which can be a simple one, like the one that we are seeing now in a desktop environment, or a most complex one, like the dynamic simulator. And then you can link together objective and subjective evaluation and select the proper data set to be used on the final output for the target setting activity. Then the next step is introducing something real into the game. And typically the first step into the real world is to put the software. So the software that controls our mechatronic system, but the software that has to be compiled as it will be in the real ECU. So this is an example of usage of an Autohook, so a real-time machine with a vehicle model running in it, and again, a driver-in-the-loop approach. Here we can put a development board inside the same loop and write down, compile the software, the final software in this development board. Then the output of the development board will be in control of a model in the loop again. The model in the loop will be the description, the mathematical description of the brake actuation system and of the brake foundation. In this way, there are a lot of stuff that can be checked. For example, you can the very basic one could be to verify if any bugs are in the software, or more than this, we can evaluate the reliability of the software and check if there are some faults. The test can be done with the driver in the loop or in an automated way. So we can open the way to functional assessment, reliability assessment, functional safety, and even the safety of the intended functionality. Focusing, for example, on an ABS logic, here you can see the difference between different tuning, and this is done just in the laboratory with a desktop simulator, trying to follow a basic straight line or move split braking maneuver, and integrating all the part of the software as a software in the loop approach. Comparing the results, you can have a grid advantage in then implementing the system with a more physical approach. And what I mean with the more physical approach? More physical approach for me means starting playing with the real hardware. So when we talk about HiL, we think about not only the ECU, but even the mechatronic hardware. This is an example of, sorry for the volume. This is an example. Probably some of you already saw these components. It is a steering test bench and a full architecture of steering, braking, and so on in the same loop. And you can see here that the vehicle is testing in a virtual scenario all the real functionalities that are embedded into the vehicle components. Here the driver is testing lane keeping, lane centering, and so on, and all the activities related to fault injection, usability of the system, control of HMI, and so on can be easily assessed here. This is an example of it. So consider that you have a real vehicle and you want to verify if your system, your HiL system, is suitable to properly assess the performance of the system from any point of view, from the performance side up to the reliability side. So you can take this vehicle, start logging some data on it, and start testing a particular feature. Here we will focus on lane centering assist system, so the one that keeps the car into the center of the lane. The approach is this one. So we take the physical vehicle, we perform the test in a closed circuit, long straight circuit, and then we repeat the same maneuver in the HiL environment with the same road 3D scanned. The HiL setup includes the real EPS in the loop, and the EPS is exchanging both electronic quantities with the virtual vehicle and physical quantities, because both ends of the steering gear are excited with the road forces. Then we have the brake system introduced into the HiL system, and also the camera. So the same ADAS camera that it is installed next to the windshield is put in the, you can see it in the picture in this slide, is put in front of a monitor just to make measurement on the lanes and possible obstacles. And these are the results. So you can see the mean error and the maximum error between the physical and virtual testing. So the test done on the real road and the test done on the virtual road. For mean error and max error, I mean the error that the vehicles makes in following the straight line, in following the midline of the lane. So you can see, for example, that at a speed of 100 kilometers per hour, the virtual vehicle is missing the middle line of the lane by 0.21 meters, and the physical one is missing the middle lane by 0.23 meters. So the difference between physical and real test is very, very low. The same can be done also can be said also for the maximum error. And so you can understand how much efficient it is to validate the system in a virtual environment using real hardware in that way. For example, typical usage of this HiL system are to inject some faults. These faults can be injected in a software way or both in electric way. For example, putting in short circuit some pin of the connectors or something like that. In that way, you can also evaluate the controllability of the vehicle and check also from some cross-domain fallback system, for example, using the brakes to help during difficult maneuver. Then you can use it also for calibration. Here we are focusing on the APS, but it is not only the only case. It can be on any kind of hardware that you can imagine. For example, dampers, semi-active dampers, the approach is almost the same. And then the things become more and more interesting when the function that you are testing is done by the interaction of different vehicle components. For example, the ADAS development that we were to the steering wheel. So the driver in the loop can take in his hand the steering wheel and directly drive the steering gear. That is the most immersive solution and can be used also in a very, very small environment like laboratories. The other approach is the one that you can see in this video, in which the steering gear is directly moved by a torque actuator, so a motor, which is acting like a virtual column. So the steering column is directly coupled to a motor, and then the driver drives a feedback unit by remote. And both feedback actuator and torque actuator are in the same control loop in order to provide the driver with the correct feedback on the steering wheel and the road actuator with the correct torque on the steering column. The same approach is used, for example, on brakes. Also, the brakes can be installed on an hardware in the loop scenario. So, leveraging on a virtual model of the vehicle, we can test all the functions that are leveraging on the brakes using the full brake system and the real brake actuator. No matter what kind of actuation system do you have, if it is a brake-by-wire system or a traditional ABS system. even in this case, the brake rig, which includes all the brake foundation, starting from the calipers to the discs, the pads, the pipes, and so on, can be driven directly connected to the driver's interface or by remote. And here we can link the feedback on the pedal feel, which is an electrohydraulic actuator put in the cockpit of the, for example, of a dynamic driving simulator, and then having on the floor a test bench in which all the brake foundation is installed together with the brake unit. In this way, for example, having a proper tuning of the calibration of the pedal feel can be easier, because you can directly change the reaction on the pedal feel in a very easy way, just acting on the software and then taking back the results for setting up the targets in the hardware side. So, as I was explaining, the most important part of the hardware in the loop side is having access not only to the interaction of the driver with the driving simulator, so not only including the driver into the loop of the simulation, but also include the hardware, and so opening the way to real testing on real components. And as I was explaining before, you can put on the floor a test bench and a driver on a dynamic platform. And this can also be done when the distance become greater, thanks to AI-based prediction techniques. And now there is a short video of how this works. Alessandro.
Thank you, Claudio. Yeah, so here we can see a dynamic driving simulator, the DIM150, that are remotely linked on an hardware-in-the-loop steering rig from Meccanica 42. The maneuvers that are performed by a human driver on the simulator that you will see includes a steering on centering filling with the small angles and the linear tire response, slalom on cones, testing balance and agility, and double lane change, evaluating maneuverability and stability. As you can see, the steering is remotely connected, and the steering movements made on the simulator are transmitted to the HiL rig, allowing investigate steering system reaction in real time. As you can see here, you have the steering robot, and these are in closed loop connection between the two systems. So, to go to conclusions. As you can see, having a hardware in the loop or in a wider range, an HiL, X in the loop, reaching then at the really end or at the beginning, but in a comprehensive mechanical hardware in the loop with the real components, leads to have human feedback in earlier. That means at the end, with the real numbers, increase innovation. For example, we have a customer that reach new records on Nürburgring, preparing that record early in advance when the prototype is still not available, or building the prototype with all the results coming from simulation. Short-term development. Some customer reach, Volvo for example, reach basically cut by half the development time for a specific vehicle, or reduce, as we said before, the physical prototypes. NIO, for example, reduced by 40% prototype production thanks to driving simulator and thanks to simulations approach. Conclusions. As you can see, and what we said in this presentation, hardware-in-the-loop applications are complement offline and driving simulator activities that help a lot the virtual sign-off. Complex use cases can be simulated and tested with the driver in the loop and hardware in the loop systems without involving physical testing with the physical vehicles, but still involving physical components in early in advance, and testing in a very dangerous conditions and simulating many different driving environments. And the Linux-based open architecture of the outo based on the concurrent real-time technology enables the integration of a custom solution as well also of the third-party products, as we see, thanks to the openness of our platform. And the outo at the end represents a complete and open solution made of by hardware, software, and integration service as well. So now we are ready for Q&A.
Thank you. Bye.